believe we have covered type of modulation. We modulate AM and FM. And also we have phase modulation, which is include under FM. Alright, so for the AM, we have covered the SBSC, conventional AM, and SSB. Alright, so I just remove the vestigial part in this type of modulation. Okay, so we have also learned what is modulating signal, or known as information, or known also as message signal. Alright, the important is we have to identify what is the carrier to be transported into our message signal. So now it will become the modulated signal, which is we will mix the carrier and also the modulating signal. Alright, so we have gone through this. For the SB signal, we just multiply the carrier and also the signal. Okay, we learn also how to find the spectrum. The bandwidth is double the total bandwidth of the message signal. Okay, we also covered this exercise, power content. Alright, so in the DSB signal, we also learn this exercise. Okay. Alright, in this exercise, we also put values for the amplitude and also the frequency. Okay, so now we calculate the power. Alright, so the second type of modulation is the conventional AM, which is this the equation AC multiplied by 1 plus MA SNT multiplied by the cos f 2 pi FCT, which is the carrier. So you have to know what is the normalized signal and also what is the modulation index. Okay, this is the modulation index. If you see the modulation index, we have different. Right, so this is the difference of 0.5 modulation, 1 modulation equal to 1, and modulation more than 1, which is 1.5. So we also learn how to get the spectrum of the conventional AM. Okay, the total bandwidth also 2 times of the message bandwidth. Okay. Right, we also see this example using signal AM cos 2 pi FMT and carrier is also cos. Okay, this is the simplest example. So we will get the not only the sideband but also the carrier. How to calculate the power of the conventional AM. Alright, so we've gone through also this example with values. Okay, now you have to plot. Alright, after plot, you can. Okay, so this is the different example. Okay, first of all, this one, if we write here AM, that's mean it already modulated. Okay, so you just have to plot the signal and calculate the power. Alright. Okay, so to find the modulation index, you know, minimum ST given divided by the amplitude. This is the formula. Okay, so for the answer, you have already the modulated signal. You just plot and then you find the carrier power here, Y15 7.5 multiplied by 2, which is the original AC. This one is already modulated. That means the AC divided by 2 and the cos we plot at positive and negative side. Okay. Right. So in conventional AM, the carrier frequency will exist, not like the DSBSC. So this is the demodulation part where you can use the envelope detector and also the filter. This is the circuit of the envelope detector and the filter. Alright. So we also have gone through this, the SSB. So for the SSB, we remove the other part, either lower or upper sideband. Okay, how we do this? By using filtering and also phasing. So for the filtering is easy. As you know, we can have a filter just to get one side only. Okay. So if you want to use the phasing method, you have to transform the signal into Hilbert transform, also the carrier using Hilbert transform. If you want the upper sideband, you use this minus sign, and lower sideband is plus sign. So in here, we will cancel out the second part of the signal. Transform do, it shifted with minus pi over 2. So sine become minus cos, and cos become. Alright, so we have also this one. I think everybody came. Okay. We then sketch the spectrum. So no more this side and this side. Alright, only one side. Okay, so for this one, we stop here. I think I explained also how to find the AC given by you carrier power. So power equivalent to AC squared divided by 2, we can have the AC. And then this is FC, so you can generate the carrier, which is AC cos 2 pi FCT. You have the AC from here and also the FC from here, and then the signal is here. So you know what is the formula for LSB, which is signal multiplied by carrier plus the Hilbert of the two of it also multiply, and then you can sketch the amplitude and phase spectrum. Okay, so this is the answer. Right, this is the formula, and then this is the spectrum. Alright, for vestigial, actually you convolve the double sideband with a filter. Alright, so it's the same concept. You have to multiply with what and what. Okay, so I decide to remove this one. So we up until SSB. Alright, so this is new, the quadrature multiplexing. In quadrature multiplexing, so what is multiplexing? Actually, we want to transmit the two signal, which is one is the original one in phase, one is we quadrature, or we move the first signal into minus 90 degree. Okay, so what we want to do in quadrature carrier multiplexing, we want to transmit two signal. Okay, so the first one is in phase, the second one is we shift using orthogonal carriers. So the carriers also we do the shifting. Okay, so we mix this one, and at the demodulator, here is the demodulator, we also do the shifting, the first signal and the second signal, and then we multiply the carrier, but don't forget the 2 because we have downgraded the amplitude by half, so multiple back by 2. 2 cos 2 pi FCT is the carrier, and then we filter one side only, and then we get the original S1T and S2T. So this is the transmitter, and then this is the receiver. So now we have the quadrature amplitude modulation. Okay, QAM. Alright, so to do the demodulation, as we know, we multiply the modulated signal by 2 cos 2 pi FCT, just shown in the block diagram before this one. And then this part, we will do the filtering. Okay. Alright, so next one is multiplexing. Okay, multiplexing is the concept of combining many signal into a composite signal, so later it can be separated at the receiving end without any distortion, of course, right? So there are many methods to do this multiplexing. So you will heard this a lot: frequency division multiplexing, time division multiplexing, code division multiplexing, and spatial multiplexing. So spatial means space, whether we have different antenna direction or we space it by different polarization. Okay, so usually in the digital signal we use TDM and CDM, but in analog we use FDM and spatial multiplexing. Okay, alright, so in frequency division multiplexing, we will divide slots, which is channel. So each channel is unique. Okay, so to prevent interference, so it will not interfere. Okay, so between the frequency and frequency, we have these guard bands. Okay, to make sure there is a very small frequency is allocated, to make sure space between them and they will not interfere between each other. Okay, so for example, in AM broadcasting, we have 535 to 1605 kilohertz. Okay, so it occupies 10 kilohertz between 535 and 1605 kilohertz. And this multiplexing will allow multiple radio signal to be transmitted over the AM amplitude modulation band. Let's say we have signal 1 with frequency 1, anything, and then the second one F2 until Fn. Okay, all this will be multiplexed here. Okay, so in one channel, so this channel can be wired or wireless, as we learned in chapter 1. And then at the demodulator part, another one we call demultiplexing. So the band pass filter will only recognize the first frequency and the second with another band pass filter and until end, right? So this process will goes to demodulator and we will get the original signal back. So a combination of these different frequency into one, we call it as multiplexing. And if we differentiate the frequency, means we using frequency division multiplexing. Okay, now we see that this F1, F2, F3, we also have these guard bands. Okay. Alright, so for example, for home number 1, we use 4, let's say 4 kilohertz also. This one, home number 2, using also 4 kilohertz frequency bandwidth. On this one also 0 to 4 frequency bandwidth. But this one is allocated at 20 to 24, the next one 20 to 28, and 28 to 32. But of course here we will put a guard bands between it. So when we transmit different frequency, and we also can separate it with a filter to make sure it has correct user number. Okay, okay, so this one, like I said, have to put a guard band about 10 kilohertz, and the frequency channel bandwidth is 10 kilohertz. Okay, so it occupies about 540 kilohertz with 1, 2, 3, 4, 5 channel plus 10 kilohertz guard band. Okay, the next one is frequency translation. Just now we combine few frequency into a channel, and now is frequency translation. That means we want to move a signal at certain frequency or from one carrier frequency to another frequency, where it can be higher frequency or lower frequency. So this frequency translation are very important and necessary or compulsory, we can say, in the design of communications transmitter and receiver. Why? Because we cannot have the same frequency receiver or transmitter at all places. So we have to translate it or move it to another frequency. Okay, so the person who do this is we call a mixer, okay, or multiplier. Or we can always see this X sign, okay, that multiplies the input bandpass signal, where usually we have RF or IF, and then we got a bandpass signal, and then by a fixed amplitude sinusoidal output from a LO. LO is the local oscillator. So this is the incoming signal RF, and then we have a mixer here, and then this local oscillator will do a sinusoidal output. Okay, alright, so this one we call it down conversion mixer. So from high frequency RF, we multiply with a LO to get intermediate frequency, which is low frequency IF. Alright, so if you want to up conversion the signal, means from low signal to higher signal, usually this is at the receiver part, this is at the transmitter part. Okay, the transmitter in the transmission line, it will be IF, low frequency, and then we transmit into higher frequency. Okay, so again we need this local oscillator to be the input of the mixer. Okay, so for example, in the first one we have RF equivalent to 80, the amplitude cos 2 pi FCT plus phase here. So LO value is V out cos 2 pi FLO, the frequency of the LO. Okay, now the mixer will be multiply, so RF multiplied by LO. So we use this multiplication, and then we will filter this part. Okay, what it say here, the mixer translate the input signal at FC to the intermediate frequency FIF. So what does it mean here? The RF will having a carrier and also the signal itself. So this IF will contains the carrier and the LO, okay, values. So we now bear in mind that IF here, the designated frequency, is equivalent to FC minus FLO. If that we call it low side injection. If IF equivalent to FLO minus FC, we call it high side injection. So what is high side injection and low side injection? That means that if the LO is higher than the FC, so we will call it high side injection, and low side injection if the LO is lower than the FC. Okay. Okay, for the low side injection, to get the IF, the input frequency FC minus 2IF will also converted into the same IF frequency. Also, for the high side injection, the IF will got the FC plus 2IF is converted to same frequency. What does it mean? So now we go to different types of communication receiver. So the first we have studied previously is modulation or demodulation. Alright, so we have this different kind of modulation. So this angle modulation we will see in chapter 5, right? So different audio sources will have different bandwidth or size. Okay, for example, our voice, the speech have 4 kilohertz, and if high or loud quality music we have 15 kilohertz. So this usually for AM its size is up to 5 kilohertz and FM up to 15 kilohertz. Okay, these are some revision, yeah. So radio system should be able to receive any type of audio simultaneously. So different station will have different sources of transmit, of course, right? So this how to differentiate this receiving or transmitting signal, we use tuner to uh, make sure we listen to the correct sources. So this all radio station will share frequency spectrum over the air, either amplitude modulation or frequency modulation. Okay, so each radio station, according to like Penang, we have different frequency. At south we have different frequency, so it's actually designated a carrier frequency, okay, where it has to transmit. Okay, as we see just now, the sharing of AM FM radio spectrum is by FDM, frequency division multiplexing. So for example, we can listen to IKIM, we can listen to Sinar, we can listen to Zayan with different frequency at different bandwidth. Okay, alright, so this is the different radio ranges. So if you can see our radio in our car, they can transmit from 88.1, I think, until the highest one 108 megahertz. Okay, so this is the AM from 540 kilohertz to 1600 kilohertz, which is very low. Okay, usually the walkie-talkie are using this frequency. Okay, so this is the radio frequency. Alright, so for AM, okay, for AM the intermediate frequency is of course it must be between this value, which is 455 kilohertz, and the FM between 10.7 megahertz. Okay, this is roughly. Right? So for a communication receiver to be receiving different type of signal, they must have some capability to extract the desired signal, where of course the noise and interfering signal is exist. Okay, so the criteria to have or to design a receiver, it must have a amplification. So this amplification will low down the noise at the end, at the front of the, to improve sensitivity. So that means it can have the ability to take only the message but lower the noise amplification. Okay, so what is sensitivity? Is a measure of receiver's ability, that means the receiving station, to receive weak signal. Okay, sometimes the signal have been traveling very far, or maybe at the transmitter power are very low, so it has to be sensitive to be able to amplify back this weak signal, as the noise will present with n but at acceptable signal to noise ratio, means the signal are very high compared to noise. So that means the receiver are very sensitive, or sensitivity are very high to receive what is the signal. Alright, the second one, or the second capability of a receiver, must have a signal selection or channel selection. So we can tune our desired signal from very wide range of frequency slot that contain other signal also, and also noise also exists. That means if we want only from 10 gigahertz to 12 gigahertz, we are capable of receiving at the desired channel, rather than like we know what the objective or the frequency that we are receiving. Okay, so this kind of selection, we call it selectivity. So that means we can select, or we are able to select a particular frequency or particular band and reject the other. For example, just now we want to just only receive 10 to 12 gigahertz, so we're able to select this frequency and reject the rest. And of course, the important part is the demodulation. If you don't know how to do this demodulation, so no point we are receiving that signal where we cannot recover the original message signal. So in order to do this, we have to know what is the carrier frequency of that transmitter. So at the receiver, we can know what to multiply. Okay, as we know, it has to be the demodulated signal multiplied by the carrier itself with the amplitude increased by the, right? So in this syllabus, we will learn three types of receiver: super heterodyne receiver, direct conversion receiver, and also low IF receiver. Okay. The first one, which is the most popular, is the super heterodyne receiver. Okay. Most of communication receivers such as AM, FM, broadcasting TV, cellular, and satellite system, they use this super heterodyne receiver. So the main idea of super heterodyne receiver, you will convert the RF signal into IF signal, alright? And then we will amplify it, of course, due to low power, and demodulate it to get the original signal back. So when we're talking about IF signal, that means this is also called a frequency translation, where we translate from RF to IF. So the process we have to do is low noise amplifier, means we remove the noise, and then remember the image reject filter, we don't want the plus to IF or minus to IF. So we put an image reject filter and then multiply with add mixer with the LO. And then now we have the new translated frequency, which is IF frequency. So this IF frequency must have a filter to ensure that we are receiving only the designated frequency. Alright, and then we go to VGA, then we demodulate it. Okay, so this is the block diagram of a super heterodyne receiver. So we have low noise amplifier, where it amplifies a weak RF signal that coming from the antenna. After traveling, we have to amplify it, but make sure the noise are low. Okay. And then the image reject filter will reject the image frequency, and together with the requester to down convert the RF signal to the IF. That means it's a part of the local oscillator to make sure that this image signal is not exist, so it will become interference at the mixer. Okay, so the local oscillator will tune a certain frequency to a desired channel. That means it will generate a frequency, and then will multiply with the mixer. Okay, IF amplifier. So after the local oscillator multiplies with the RF signal after LNA, so it now the frequency will become IF. Okay, so IF amplifier will amplify the IF signal up to 10 to the power of 6 and reject adjacent channel signal and interference. So this part will do the frequency selectivity, where we only want the selected frequency for IF. Alright, so but the bandwidth will the same as the signals, where the signal is the RF. Alright, so the automatic gain control AGC will adjust the IF amplifier gain or increase the gain according to the signal level. So this will keep the average signal amplitude almost constant. That means we make sure the amplitude can be read, alright, at a certain IF frequency, right? And then the demodulator will demodulates or recover the message signal. Alright, so let's see this example. Example in Messiah books. So, a super heterodyne receiver. Okay, it will cover or receive an RF frequency from 45 MHz to 860 MHz. So this is very high frequency, 45 to 860, and channel spacing of 8 MHz and IF of 40 MHz. Alright, so assume this is high side injection, which means the LO is going to be higher than the RF. Okay, the question is, if the receiver down converts the RF signal to an targeted IF of 40 MHz as stated here, calculate the range of frequency for the LO. So we know that to calculate the LO, we must identify what is the IF that we want. Okay, and then we also know what is the range of RF signal that will come to the mixer. Okay, that is one. So we know the frequency, the calculation using FLO equivalent to FIF minus FRF. Okay, and the next one is calculate the range of image frequency. We know that this one will come at plus 2IF of the LO. Right. So later if we do these two exercise, we will note that the image frequency will overlap with the signal from 45 to 860. Okay, so this is cannot be acceptable. So we want to test 1.2 gigahertz IF, okay, which is higher, very high. Alright, now we want to do the next. Like just like this one, we have to calculate the LO and then find the image and then check whether it's overlap the image and the signal band. Okay, so inshallah very easy. Now we want to find the LO values. Since we know the incoming RF signal is 45 megahertz and the desired IF is 40 megahertz, so we have to prepare the LO from 85 megahertz until 900 megahertz. Okay, so the next question, there will be image. The image will be at plus 2 IF. Okay, so what the IF? 40 times 2 will become 80. The incoming RF frequency is 45. So that means at 125 megahertz there will exist an image, and also the next at the other end is 860 plus 2IF, so 940 megahertz is the image frequency. So if you can see here, okay, this is 85, okay, and then this is 900. So the image that we don't want, so this is 85, is more or less is here, image 125. This is at 2IF or image frequency F image, which we don't want it, this one. So what we do, we want to up conversion to 1.2. We down convert it into a below IF. So here to write down receiver, we have to convert the RF into IF. Okay, and the value of LO can be calculated with the incoming signal and also the allocated IF. So using direct conversion receiver or DCR, we don't refer to any IF. So it is also called zero IF. The same concept where we also need an LO, local oscillator, but the local oscillator will use a frequency that is identical or very close to the carrier or intended signal. Okay, that's mean the IF is 0. Okay, so it also called homodyne or synchrodyne or zero IF receiver. Okay, so this approach, since we don't have an IF, we will save from the problem of image filter, or no need to use image rejection. Using the value of IF, the DCR 0 IF, and this one low IF. Alright, so we are going to conclude the type of modulation: DSB, conventional AM, SSB. This one SSB plus carrier, and VSB also we have in the slide, but we are not covering for our syllabus. Okay, so this is the difference of bandwidth transmission. So this one on double, and this three will be two. This two will be 2B, and VSB will have some efficiency here. Small f is added. Okay. And then this is the formula for DSB for amplitude modulation. For single sideband SSB, the yellow one, and VSB.